Hey YouTube, we're back. Day 3 of our quarantine distance learning. Hope you're still doing well. Please remember that you can always reach out to any of us. We're dedicated to helping you and making sure that this whole situation doesn't affect you terribly. We will continue with our lessons from Mr. Boothman, who will come on camera in just a second. Please make sure you're doing your work. Please, we're putting in so much time and effort into this. It would be a shame if you didn't take advantage of everything that we're doing. All right, so let's get Mr. Boothman here. Let's begin. All right, happy Friday. It is College Friday. Okay, I'm wearing Northwestern purple. Feel free to ask me any of your college questions during our Google Meet session later today. I know you probably have questions specific to our current situation. I'm not going to be a ton of help with those, but even if you just need to talk stuff out or express concerns, just know that I'm here. Maintain a bit of normalcy for you. Brief announcements for the day. Your exit ticket today is going to be much like it was our first day of these online lessons. Just submit a question from today's lesson that you might have. I'm going to look at those and we'll address those during our Google Meet on Monday. That will be due by midnight tonight. In addition to your AP Classroom assignment that was assigned a couple of weeks ago, you've had ample time to complete that. I will be putting those in as completion grades. If you do not submit it by midnight tonight, then it will be going in as a 0, and then I'll reach out to you and we'll talk about getting that done. Okay. All right, now let's jump back in. Now, if you remember, on Wednesday when we started our notes for this section, I had mentioned that there were 2 ways of finding these error bounds. The first was knowing that that remainder term must be less than or equal to the largest possible next term in the series, right? That's where we found the max of the next derivative times x minus a to the nth power divided by n factorial, okay? And that was the Lagrange error bound. The second method for evaluating these error bounds, for finding how accurate these approximations will be, okay, is, it's going to be a more specific case. So let's continue in our notes. This is 10.4 continued. And our second method here. Okay, so wherever you started that other one, you put 1. Here's number 2. For a Taylor polynomial, whose terms are both, now this is important, both alternating and decreasing. We'll talk about what this means in a second. The maximum error for the approximation at a given value is equal to the value of the first unused term. So feel free to pause, take a second, write that down. For a Taylor polynomial, not a Taylor series, we're stopping at a specific term. For a Taylor polynomial whose terms are both alternating and decreasing. So here's what that looks like. I'm just going to give you an example of that. We're starting with 1 plus 1/2 minus, should be minus 1/2 plus 1/4 minus 1/8 plus 1/16 minus, and so on. So our signs are alternating. That's what alternating means. The sign is alternating. And if we were looking at the nth term formula for this series, then remember we denote that using -1 to the nth term or the n minus 1th term to get us to alternate that sign. And each subsequent term is smaller than the term before it, so it is a decreasing series. Notice 1/2 is smaller than 1, 1/4 is smaller than 1/2, and so on. So for a Taylor polynomial whose terms are both alternating and decreasing, both conditions must apply. Then the maximum error for the approximation, and here's where this differs a little as well, for the approximation of a given value. So not just in general, how accurate is this polynomial going to be, but if I plug in this number for x, how accurate is that number that I'm getting back? The maximum error there is going to be equal to the value of the first unused term in our Taylor polynomial. Okay. One other way of visualizing this, I really like this visualization. Imagine here we have a number line. Here is our actual value for some f of a. Okay. Here is our first term. Here is our second term. Here is our third term and our fourth term. So we're starting here. Notice that the signs of each term are alternating. And we're getting smaller. So the maximum error we could have here, if we stopped at this term, for example, would be equal to this next term in the series. Okay, and we can see that it couldn't possibly be any bigger. I just really like this visualization of it. We're alternating, jumping back and forth, and our terms are decreasing. So we're getting closer and closer and closer to our function value. I would like to do some examples. In fact, I'd like to do 2 of them. Once we start doing examples, like most things, I think it gets a little easier, even if conceptually it's still difficult for you. Once you see what we're doing, I think it makes a little more sense. Okay. So let's look at this first example here on page 3 in our mastery sheet. Again, those first 2 pages should be completed. The function g has derivatives of all orders, and the Maclaurin series for g is given by this infinite sum, and they list the first few terms in the series for us. The Maclaurin series for g evaluated at x equals 1/2 is an alternating series whose terms decrease in absolute value to 0. The approximation for g of 1/2 using the first 2 non-zero terms of the series is 17/120. Show that this approximation differs from g of 1/2 by less than 1/200. 2 very, very, very important things about this problem. First, it is explicitly stated that this Maclaurin series is both alternating and decreasing. Because of that, we know that this approximation must differ by less than the next term in the series, by less than the value of the first unused term. Because it is alternating and decreasing. It has to be doing both. And the first unused term, okay, it tells us that the approximation for g of 1/2 using the first 2 non-zero terms of the series is 17/120. So the next term, the first unused term, must be the third term. Okay. At x equals 1/2. So we're going to evaluate at 1/2. What is the third term of this series? Well, it's actually already written out for us. It's x to the 5th over 7. At x equals 1/2, that's 1/2 to the 5th power all over 7, 1/32 all over 7, which is 1/224. Is 1/224 less than 1/200? Yes, it is. So since the series is alternating and decreasing, approximation must differ by less than 1 over 224, which itself is less than 1 over 200. That's it. Fairly straightforward. There's just a lot to think about, as with all of these calculus problems. I want to do one more example together, which is the rest of this page, and then I will ask you over the weekend and on Monday in class to work on the last page of this mastery sheet. Okay, there won't be any new notes on Monday. That will be it for 10.4. Okay, so for now, let's finish this other problem here. Number 2, let f of x equal the natural log of 1 plus x cubed. Part A, find the first 4 non-zero terms of the series for f of x and use them to approximate the value of f of 1. All right, do we know, we could calculate this general Taylor series for this function, or if you've memorized the Maclaurin series, then you know that the Maclaurin series for the natural log of 1 plus x is fairly straightforward. Instead of x, we're doing x cubed. So the Maclaurin series, where x is x cubed, equals, and we're looking at the first 4 terms, x cubed minus x cubed squared over 2 plus x cubed cubed over 3 minus x cubed to the 4th over 4. At f of 1, or approximating f of 1, we're going to plug in 1 here. We got 1 cubed, which is 1, minus 1 cubed squared is still 1 all over 2, plus 1 cubed cubed over 3, minus 1 cubed to the 4th over 4. And getting common denominators, adding all of this together, we get a value of 7 over 12. So the first 4 terms of the Maclaurin series for this function approximates f of 1 as 7 over 12. This is a question I could have asked you a couple of weeks ago. Okay. Part B is where things now get a little more interesting. Show that the approximation found in this part A differs from the actual value of f of 1 by less than 21 over 100. Well, looking at this series, our Maclaurin series, it is both alternating and it's decreasing, right? Each term is getting smaller. Since it's an alternating and decreasing series, the approximation must differ from the actual value by less than, well, what's the first unused term in the series? That means we need the next term, in this case, the 5th term of our Maclaurin series, which would be x cubed to the 5th all over 5. Plugging in x equals 1, this is 1 over 5, which is less than 21 over 100. Okay. 1 over 5, think of that as 20 over 100. That's less than 21 over 100. So we're done. All because this series was both alternating and decreasing. So when our series is alternating and decreasing, I hope that is something that we learn to watch out for, because it makes our error, our approximation error, much easier to calculate. It's just the next term in the series, okay? That is as far as I wanted to go in today's lesson together. Again, over the weekend, I would like you to get started on the last page of this mastery sheet, but I will give you all of Monday to work on that as well, okay? So your work, your tasks for the rest of today. Submit the exit ticket, which is a question from today's lesson, by midnight. AP Classroom is due by midnight, and then work on the rest of the mastery sheet. That will be due by the end of the day on Friday, just for completion. We'll go through some of those additional problems together as well. Okay. All right, let me know if you have any questions. All right, well, that's it for today. Please enjoy your weekend. Please let us know if you need absolutely anything, and make sure you hit that like and subscribe button.